Hi, my name is Abhinav, and I'll talk to you about Open Data Domain Specification, or OpenDDS. So, what is OpenDDS? It's a specification for modeling a data and API graph for your business domain. You can define what objects exist in your data domain, where do they come from, what are the relationships between these objects, and what access control and APIs you want over them. The metadata for Hasura version 3 follows OpenDDS. It supports the OpenDDS specification, plus has some more Hasura-specific configuration. But what is the benefit of OpenDDS? Well, OpenDDS acts as a single source of truth for all your data. It is API or model first. That is, you can reason about your data models and API contracts independent of your actual databases. As a result, OpenDDS, and by extension the metadata for Hasura version 3, is also completely stateless. The same metadata configuration will always result in the same API contract and the same Hasura semantics, even if your underlying data sources have completely changed. So let's get right into it. In the next few slides, we will go over the main concepts in OpenDDS and how they come together to define your data domain and APIs. Please note that the examples you see in this talk may have been slightly modified for brevity. So first up are types, and this includes your core domain objects. Types are a core building block of OpenDDS. Every bit of data that flows through OpenDDS has a type. This includes primitive types like integers and strings, type containers like nullables and arrays, and user-defined types. For instance, consider an e-commerce application. In their domain, product would be a reasonable object type, and you can see a sample definition for it in the example on your right. This product type has fields like ID, name, category, etc., and each field has a type. The types of these fields must also be valid OpenDDS types, either primitive types like string or integer, or custom types like UUID. They can also use type containers like nullable, which means the field may not be present on the object, or array, which means this field can have multiple values. In our example, the category ID is nullable because a product may be uncategorized, and the tags field is an array since a product may have multiple tags. Additionally, object fields can also have arguments that can change the output behavior of the field. In our example, the shipping cost field takes an argument for zip code of type string, and this zip code can affect the value of the shipping cost field. Later in the talk, we will also see how we can define validation rules to ensure that such a zip code argument received as input from a user conforms to a particular format. OpenDDS also supports type inheritance, in which case all fields of the base type get inherited. In this example, discounted product inherits from product, so it gets all the fields of the product type, and also has an extra field for the discount, which the product type does not have. Next up are models. Models are the primary mechanism of accessing data inside OpenDDS. A model is defined as a logical collection of objects of a certain type. Now, this may be backed by a real database table, or an ad hoc SQL query, or some custom APIs, or even by mock data. In Hasura's implementation of OpenDDS, you can specify how a model maps to the underlying data source, including mapping any field names to potentially different column names in the raw data source. However, this mapping is required only for actual query execution, and the rest of OpenDDS, including your final API contract, is agnostic of the model source. In the example on your right, the all products model comes from a Postgres table called products in the public schema, and the best-selling products model comes from a custom SQL query on the same Postgres database. The configuration for the Postgres database itself, like its connection string, is defined in Hasura's metadata which is an extension of OpenDDS. In OpenDDS, models can also take arguments. Like the best-selling products model, in our example, takes an argument that defines the sales threshold for a product to qualify as best-selling. Models also enable or disable specific capabilities, like insertion, deletion, pagination, aggregation, sorting, etc. For example, for a model that's backed by a read-only view or an ad hoc SQL query, you probably want to disable all mutations. Apart from models, commands are the other way of accessing concrete data. A command is simply a custom function, or lambda, that is defined by input arguments and an output type. The actual semantics of the command itself are opaque to the OpenDDS specification. A command can be backed by a custom API endpoint, like REST, GraphQL, gRPC, etc. Commands are useful for importing custom APIs, like remote actions or remote schemas in Hasura version 2. Commands can then either be used directly from the eventual data API that you will create, or from within DDS itself, like for relationships or authorization rules. In the example shown here, checkout cart is a command which contains some business logic to complete the checkout process. It takes as input a card ID and a payment method and returns a result of the checkout. GetWeather is also a command that takes as input some location coordinates and returns the temperature at that location. Note that the source for this command is defined as a specific query root field in a remote schema. Next up are relationships. Relationships in OpenDDS define that given an object of a certain type, how to find related objects by invoking a particular model or a command. As a part of the relationship definition, you can define how various fields in the source type map to either a filterable field on the target model or to an argument on the target model or command. In the example shown here, the relationship called product reviews defines that given an object of type product, we can find related objects in the reviews model by using the ID field of the product object for filtering the reviews model using its product ID field. And there's also the city weather relationship that defines that given an object of type city, we can find the related weather object by calling the getWeather command and passing the city's location fields as arguments to the getWeather command. Typically, you would only want non-mutating commands like getWeather on the target end of your relationships. Role-based access control is natively supported by OpenDDS. For each role, you can specify permissions for different OpenDDS concepts. For instance, for an object type like product, you can specify which fields are selectable for a given role. In this example, we have defined that the seller role is only allowed to select the ID, name, and sales fields of the product type. For models that are filterable, you can specify which elements or rows in the model can be selected, updated, or deleted by a given role. Or if you want, you can disable these operations altogether. In our example, the seller role can only select those products whose seller ID equals a given session variable. For any operations requiring external input, such as command arguments or field arguments, you can configure input presets and input validation. In this example, when the seller role is inserting into the model, they can only specify the name field, and the seller ID field is automatically set to the currently logged in seller's ID. Predicates are a key part of defining authorization rules, whether it is for model filters or for input validation. OpenDDS supports two types of predicates: model predicates and inbuilt predicates. Model predicates are used for filter permissions on filterable models. They use special operators defined by the scalar types of model fields and are pushed down for execution to the underlying database. On the other hand, inbuilt predicates use inbuilt OpenDDS operators, and in the case of Hasura, are executed within the Hasura server itself. These operators are used for input validation. A very powerful feature of OpenDDS is that it also allows arbitrarily composable value expressions for use in presets and predicates. For example, here we have a validation rule for a credit card number. It says that the card owner must be the currently logged in user, specified by the session variable, and it finds the card's owner by following a previously defined relationship called card owner. Then, the rule says that the card number should have exactly 16 digits, using the inbuilt regular expression operator. Finally, the rule validates that the card belongs to the MasterCard network by calling a custom command to get the network of the input credit card number. Once you have defined your data graph, OpenDDS lets you customize and configure APIs over that data. This example is configuring a GraphQL API. It first specifies that the OpenDDS type, called product, should map to a GraphQL interface, also called product. One OpenDDS type can have at most one GraphQL type. Then, over the products model, it configures a query root field called product by ID, which filters the model using the ID field. Then, it configures query and mutation root fields for a general product select API and a general products insert API. Finally, it also configures a simple mutation API over the card checkout command. Anything that is specific to an API format, like GraphQL or RESTified endpoints, is isolated to this part of the configuration, leaving the rest of OpenDDS agnostic of any target API format. That's it. There's a lot more to OpenDDS than what was possible to cover in this talk. So if you would like to learn more, or even better, contribute to the future of OpenDDS, please check out the GitHub repository and feel free to reach out with any questions. Thanks a lot for watching.